Hello, friends. There's a fuse on the switching power supply. It's usually located at this input position. If this fuse blows, we need to check the switching power supply to see if there's any damage to the other components behind it. So we can't just directly install this fuse and test the device. That might cause the fuse to blow again, which could then burn out the components behind it. So after the fuse burns out, which other components in the back might be damaged? Let's briefly discuss this in our video. First, we have this piece here. It's a fairly simple switching power supply board. And the other one is a power board from an LCD TV. So first, we'll start with this one. Let's briefly explain. Now, since this fuse, it burned out. That indicates there's a high current in the output stage, or it could be interpreted as a short circuit. That's what would cause this to happen. The current exceeds the capacity of the fuse, and thus it burned out. So we need to consider the following. First, the power input is 220 volts. Then it goes to this rectifier bridge. At the front end, it's all 220 volts. So we need to consider these two 220 volts lines. That's between the live and neutral wires, whether there's a short circuit between them. If that's the case, we'll look at which components are connected in parallel. So we can see that the fuse is connected in series. It experienced high current and burned out. This part is a varistor. This varistor acts as lightning protection. The varistor provides lightning protection. He's connected between the live and neutral wires. So what about its damage? It's possible that if it breaks down, it would cause a short circuit between the live and neutral wires. This would cause the fuse to blow. There's also a thermistor here. The thermistor is connected in series, so its damage won't cause the fuse to blow. This is where we can see this area. This area is full of inductors, including this location. These two spots are capacitors. As for the inductor, let's look at the circuit traces on the back. We can see this place. This is a small inductor coming through here. Here's another set of small inductors coming through here. Moving further along, we can see that this is an inductor all the way. This is also an inductor all the way. They are all connected in series on this live wire, the fire wire and neutral wire, so it's burned out. It's damaged then. It won't cause a short circuit in this circuit. But we can see. So here, these two capacitors are X capacitors. These two capacitors, once damaged, we can see they're connected between the fire wire and neutral wire. If this capacitor is shorted, it will also cause the fuse to burn out. That's why we need to carefully check these capacitors here as well. Of course, the possibility of these capacitors being damaged is not very high, because these are two safety-rated capacitors. And then there's this part. We can see several of these resistors. Surface mount resistors. The resistance value is very high, and several are used to increase its voltage tolerance. These resistors serve the purpose of discharging the capacitor after we power it down. Even after powering off, the capacitor will still hold a charge. This is to prevent it from causing harm to the human body and avoid electrocution. So we use these resistors to safely discharge the electricity. As we just mentioned, if those two components are damaged, it could cause the fuse to blow. Let's move on further. So here, in front of this rectifier bridge, we have 220 volts. And then beyond that, after passing through this rectifier bridge and reaching this point, with this capacitor added, we now have a voltage of 300 volts. If we explain it using this version, it's relatively straightforward. We can see it's quite simple. This 300-volt point on the circuit board, it's here. That is, after going through this bridge rectifier, it's then filtered. The capacitor is in this position. After that, there's a 300-volt DC. Moving further along, let's see where it goes. With this 300 volts, it will reach here. This is the position of the switching transistor. It reaches this position of the switching transistor. Getting to this switching transistor, if this switching transistor is damaged, it has broken down. After breaking down, the 300 volts will pass through this switching transistor, from its drain to its source, then through this small current-limiting resistor here, reaching this negative terminal. When it reaches the negative terminal, the current becomes very high. It's extremely high. This will cause the fuse to blow. There's another scenario. It's further back. Here's this optocoupler. So this optocoupler, we know it serves as an isolation function. This is the isolation part. It's designed to affect the output voltage at the back. We provide voltage feedback. It also acts as a voltage stabilizer. Now, for the circuit behind it. If this output voltage is high, we feed it back to the power chip to lower the duty cycle of its output. What if the voltage at the back is low? Then we use this optocoupler to feed the voltage back, to increase the duty cycle of the chip's output. So it serves as a regulating function. If this component, the optocoupler, gets damaged, when the voltage at the back suddenly rises, it won't send a signal to the chip. As for the chip, its duty cycle will remain relatively high. When the duty cycle is higher, it means that the magnetization time for this coil is relatively long. Once the magnetization time is longer, the current flowing through it is higher. If it is higher, then the fuse is also subject to change. As for this voltage regulator here, if it is damaged, it may also cause the fuse to blow. Furthermore, this does not use that type of voltage regulator, but instead uses TR-431. One of the functions of this TR-431 is similar to it. Once this TR-431 is damaged, it is the same as the optical feedback we discussed earlier. It also fails to provide voltage feedback to the chip. So once the chip does not receive feedback from the voltage behind it, it will continue to rise. In principle, the chip will cause the voltage behind it. This voltage continues to rise. But one consequence of its continued rise is, so that means here in the front, the duty cycle of the output is continuously increasing. This means it's getting an excessive boost. That could also cause the fuse to blow. So, once the fuse is damaged, we need to consider these points. All of these need to be considered. We should also consider the rectifier bridge on this board. Here it is. This switching transistor needs to be considered too. Then there's this optocoupler. And this 4N3 or this MOSFET. It can also get damaged. Additionally, as we mentioned earlier, on a board like this, higher quality boards have some protective components, like this sub-ohm resistor. If this breaks, we need to consider that as well. And there's also the X capacitor, and these other components can cause the fuse to blow. All right, folks. That's all I have to share in this video. Thank you for watching. Goodbye.